Okay, so let's try the first one. So, is this ionic or is this molecular? What do you think? Okay, why? How do you know it's ionic? Convince me. Okay, yes, right? See, it's got aluminum. Aluminum's a metal, so this is ion. I'm going to put a little I there. So that means we name the cation, we name the anion. We don't use those prefixes on this one. So how would I name Al? Just aluminum. Does aluminum need a Roman numeral? So pull out your periodic table if you haven't yet. It does not need a Roman numeral. Why not? It's in the magic triangle, yes. So its charge does not change. How would I name sulfur? Just a nonmetal by itself, not combined with any other elements. That's when they end in "ide." So sulfide, right. Nonmetal, right, not combined with oxygens or anything. So "ide." That's it. Aluminum sulfide. How about P2O5? Is that an ionic compound or is it a molecular compound? Okay, convince me. Why is it molecular? Because phosphorus and oxygen are both in the top right quadrant, right? They're both nonmetals. Okay, so that means this is where we're going to use those prefixes. So how would I say two phosphoruses? Diphosphorus. Let's make sure we spell phosphorus right. It's R-U-S, not O-U-S, by the way. No O-U-S. And 5 oxygens. Pentaoxide, right. Good. Okay. How about the next one? Is that ionic or is that molecular? Convince me. Because copper is a metal and OH is a polyatomic ion, so it must be ionic. Okay, so yes, C used copper. Does copper need a Roman numeral?
Yes.
Why? It's not in group 1, it's not in group 2, it's not in the magic triangle. Okay, so we'll figure it out from whatever that other thing is. What's OH called? Hydroxide. What is the charge on hydroxide? 1 negative, or just negative. I have 2 of them, so that's a total of 2 negatives. So if the anions are 2 negatives, the cations must be 2 positive. And I have 1 copper, so that 1 copper must be 2 positives. I would name it copper 2 hydroxide. All right? Okay, your turn. Try the next 4 there and talk it over with your neighbor. See what you guys think. Help each other out. Compare answers. Don't be a loner. Help somebody out. Wait a minute. So first figure out, is it ionic or molecular? That's the first thing to figure out. And then you can know which scheme to use for naming it. You don't use it if the first element is just 1.
Okay.
Only that the second one is 1.
Okay.
So yeah, you wouldn't say monocarbon monoxide. You would just say carbon monoxide. The second one gets the mono, the first one doesn't. Okay, talk it over with somebody. See what they got for K2O. What did they get for CS2? Find somebody around you, next to you, behind you, in front of you. Help each other out. Compare and contrast. See what you guys think.
Carbon disulfide.
And no metals and no polyatomic. If you see a metal, or you see one of these, just automatically. Practice, practice. Make a second language for you.
I wanted to ask you about homework. There was a question that it was silicate, and we're supposed to write the formula for it.
Oh, okay.
Yeah, you don't know how to do silicate, do you?
Okay. Okay, which number is that? I could go on there. I can change it or something. I can't change it, but I can make a little note or drop it. Basically, it's going to be this silicon. I'll tell you, silicon's right under carbon. You know, carbonate is CO3 2 negative. Silicate is SiO3 2 negative.
Okay.
It's the exact same pattern, but which one it is?
It's 5.2.
Okay. Okay. Send me an email if you would, just remind me.
Yeah, definitely.
Send me an email, yeah, send me an email. Yeah, it's 5.28 and it says silicate, and I'll make a little note to.
What was your email?
K McCorkle@miracosta.edu. You put McCorkle and K and C or something like that. Okay, so do you and your partner agree? If not, help each other out. Did you get through them all? Oh. Check that one out.
Two. So that second one I think is by itself. This is different. But yeah, I put this is capital C, capital O.
Okay, well, let's go over these real quick then. See what we can do. So, I'm going to clear this off and keep going here. So, oops. So D, K2O, is that ionic or molecular? Ionic has potassium, right, which is a metal. So K is potassium. Does that need a Roman numeral?
No.
Why not? It's in group 1, so it's always 1 plus. It doesn't ever vary. O, so oxygen, non-metal, all by itself, not combined with anything else. Oxide means it ends in "ide." It's all by itself, right? It's not combined with anything. It's not like oxygen or something else. Okay, next one. Ionic or molecular? Molecular, right. Carbon and sulfur are both non-metals. So how would I name that? Carbon, right? And again, you don't use mono if the first one's only one. And 2 sulfurs, disulfide, correct. Awesome. NH4 and then CO3. Ionic or molecular? That is ionic. Now, it's a little confusing because they are all non-metals, but you should immediately think, oh, that's a polyatomic, that's a polyatomic. So there's an ion, so it's got to be ionic, yes. So how would I name that? Ammonium is the first thing. And what's CO3? Yeah, it's ionic, so no mono, di, tri, or anything, just ammonium and then carbonate. Because carbonate is CO3. So what carbonate is, ammonium is NH4. Just name the cation, name the anion. You don't use mono, you don't use di, tri, whatever, it's molecular ones. G, is that ionic or molecular? Ionic, because it's got a metal and it's got a polyatomic. So Fe is called what? Does iron need a Roman numeral? Yes, it's not in group 1, 2 of the triangle. So let's figure it out. What's this other thing called? Acetate. Yes. What's the charge on acetate? It's negative. And we have 3 of them, so that's 3 negative. So all of the irons must be 3 positive. And there's only 1 iron, so that 1 iron must be 3 positive. So iron 3 acetate. Great. Yes.
For P, why would we not put a mono in front of the oxide? Because there's only one of them.
Because it's not a molecular compound.
Okay.
Only the ionic compounds. I mean, only moleculars get mono, dis, tris. Ionic, you just name potassium oxide. So it's not dipotassium. It's not monoxide. Only moleculars get that. Yes, it's a very common. It's a very common. What's the word? Confusion on these. Yeah. So make sure only if it's non-metals do you use the mono, di, tri. If you have polyatomics, you have metals, don't use that. Okay. Well, that's pretty much all we're going to say about naming for right now. But I will tell you again, like I said before, naming is probably the second biggest thing we do this semester after the unit conversion stuff. So naming is going to haunt you the rest of the semester. So you really have to practice the heck out of this naming, because the next chapter then after this, we're going to get into writing equations, and I'm going to say to you, okay, so write the equation between let's say iron 3 acetate and it's aluminum sulfide. That's all gibberish to you. You don't know how to even write the formula, so you can't balance the equation or anything. So you really have to know how to speak the language in a sense, okay? So I'm telling you, practice this. So there are, again, I mentioned on YouTube, all kinds of videos for this kind of stuff. Also on Blackboard, if you go onto Blackboard, I have put a bunch of links on there on some other little things. So if you go to, under Content, there's a folder that says Nomenclature Activities. And nomenclature is the fancy word for naming. And I have links to all kinds of little games and practice little flashcards on naming. It will just quiz you over and over and over out on how to name. So I'm telling you, go in that folder and just name molecular ones over and over one. Name and the ionics, just name them over and over and over. And eventually, like I said, you'll know it. I mean, it really is kind of like a foreign language in a sense. Right, just learning how to speak chemistry, and eventually it'll just roll off the tongue. Oh yeah, it's K2O, CS2, and it'll just fly off the tongue. But okay, well, let's try a few the other way. So now here's the name. You give me the formula. So I'll do the first couple with you again. So lead Roman numeral 2. So what's lead symbol? PB. What's the Roman numeral 2 mean?
2+.
It's 2+. Okay. Chloride. What does "ide" tell you? Yeah, just the nonmetal by itself. So just chlorine by itself, not with any oxygen. So what would the charge on chloride be? So you find it on your periodic table, and you see it's 1 away, so it's 1 negative, right? It's 1 away from the noble gases, so it's just a single negative. So how would I make a 2+ and a 1 negative balance out? Yes, I need Pb, but I need 2 of those chlorides, so PbCO2. So now the 2 negatives balance out the 2 positives, right? Okay, magnesium. So find magnesium on your table. What's the symbol for magnesium? Mg. So what's the charge?
2+.
It's number 12, I think, or something, right? So it's in group 2, so it's 2+. Now what does ite tell you? Not "ide." What does ite mean? It lost an oxygen. Okay, yeah. So what's phosphate? Phosphate's one of those 10 you learned. Phosphate is PO4, 3 negative. So what's phosphite then? PO3, 3 negative. Don't change the charge. Just lose an oxygen. Awesome. So I've got a 2+ and a 3 negative. How can I make a 2+ and a 3 negative balance out? So make them both into 6, right? Right? Because 6 is at least called multiple. So I need 3 of these, I heard you saying, and then I need 2 of these. So how would I write that? Mg3 parentheses PO3 parentheses and then a 2. Right, exactly. Does that make sense? So the 3 magnesiums makes a 6 plus, the 2 phosphites makes a 6 minus. Now they balance out. Okay, I'll do one more with you. Nitrogen triiodide, how would I do that? This one's easy. Just Ni3. It must be molecular because I see a tri in there. All right? So just nitrogen and 3 iodines, what's telling you. Yeah, so if you see those mono, di, tri, there's no charges to worry about. It's not ionic, it's just molecular. So it's just, nitrogen, triiodide, 3 iodines. Okay, your turn. Try the next 4 or 5 there. I guess there's 5. And then help each other out, talk it over, ask questions, ask me questions. So, tin 4 oxide. So tin, what's the symbol for tin? SN. And the 4 means 4 plus. Oxide, non-metal by itself. So oxygen all by itself. What's the charge going to be? 2 negative. Okay. Now sometimes I know students will do the crossover rule first here. And they'll do SN2O4. But you can't stop there. Why not? Why is that wrong? Because you got to reduce 2 to 4 down to the simplest ratio, which is 1 to 2. So 2 negatives makes 4 negatives, bounce out that 4 plus, so 1 to 2. Okay, calcium nitride. So calcium, you find calcium. It's in group 2, so it's 2 plus. Nitride, ide again. That means non-metal by itself, right? So you find nitrogen on the table, and it's 3 away, so 3 negative. So how do I make it 2 plus and a 3 negative? 3 calciums and 2. Right. Okay, dichlorine heptaoxide. Okay, I see the prefixes, so it's just a simple number of just knowing what di and hepta mean. So what's dichlorine? CO2. What's heptaoxide? O7. Hexa is 6. Hepta is 7. Sodium, hydrogen carbonate. So sodium's in group 1, so it's 1 plus. Hydrogen carbonate's one of those ones you had to learn. What's hydrogen carbonate? HCO3 negative. So you put those together in just 1 plus, 1 negative, just put them right together. NaHCO3. Okay. Barium. So barium is in group 2, so it's 2 plus. Phosphide, again, ide, non-metal all by itself. So phosphorus all by itself. What's the charge on phosphide? 3 negative. So how do I make those balance out? What do I do? Ba what? Ba3, P2. Awesome. Okay, I'm telling you, go practice these, practice these, practice these. It may make sense right now, but I'm telling you, you got to practice it. Keep practicing it, right? And just drill it in your head. Just like you're trying to learn a foreign language. I mean, literally, just practice it, practice it, practice it, practice it. You can't just wait till the night before your trip to Spain and try to learn Spanish, right? Right? Or your test in chemistry, try to learn chemistry. You got to practice it, practice it, practice. I'm telling you, watch the videos, do the little games. I mean, just make it fun. If you just do whatever you have to do like that. Okay, well, let's move on. We still got a lot of ground to cover here. So, just real quickly, as a little review. Two kinds of bonding. Ionic bonding, that's where we're transferring electrons, right? The metal gives an electron and becomes the positive cation. The nonmetal takes the electron, becomes the negative anion. And then there are the covalent or the molecular compounds where you're sharing electrons. I want to spend a little bit more time here on the covalent bonds and those structures, which is what our lab is all about, drawing the structures of a bunch of molecular compounds. So, okay, so I'm going to review this because this already has. Okay, so again, metals transfer, nonmetals accept. So let's say again, you're making a compound between sodium and chlorine. So if you find sodium on your table, it's in group 1, so that means it's got one valence electron. If you were going to draw the Lewis dot structure for sodium, you would just draw sodium with a single dot, right? Chlorine is in group 7A, so it has 7 valence electrons. So you would put 2, 4, 6, 7, right, around it like that. Well, now then try to put them together into a compound. Well, we said for ionic compounds, the metals want to lose as many as they can in order to have the noble gas configuration. The nonmetals want to gain. So you know sodium wants to lose one, right? Chlorine wants to gain one. So perfect. So sodium just gives its extra one over here to chlorine. And it becomes positive. And now it has the same configuration as neon. Chlorine has gained one, has the same configuration as argon. They're both happy. So that's the way it works again for the ionic compounds. One loses, one gains. Well, what if it was sodium and oxygen? Well, oxygen, you know, needs 2 more electrons, right? It's too short. So oxygen has in a sense 2 little vacancies in its octet. So one sodium comes in and fills in the one vacancy, another sodium comes in and fills in the other vacancy, and then in the end, each sodium is happy and the oxygen is happy. We've made a nice neutral compound. So that's how it works with the ionic compound. So again, we're just transferring electrons. Okay. So let me show you the molecular compounds. I want to spend a little time on those. Okay, so now we're going to look at sharing the electrons. So remember, molecular are just nonmetals, right? So 2 nonmetals. They're going to share them. So I'm giving examples. Let's look at hydrogen and oxygen. So molecular compounds are going to share electrons. So now, like I said, these are both nonmetals, so it's not like the hydrogen is going to lose and the oxygen is going to gain. They're just going to each share until they get a noble gas configuration. So how many more electrons does hydrogen need in order for it to be like the noble gas that it's nearest to?
2.
Hydrogen is a nonmetal. It will not lose any. How many does it need to gain? Not 7. Where's hydrogen on your table? Find it on your table. How many more will it need in order to be like a noble gas? It needs to be 1, and then it becomes like helium, right? So hydrogen just needs 1 to be like helium. Oxygen needs how many more? It has 2 openings, right? So it needs 2 more. Yeah. Okay, so what would happen then? Okay, so one hydrogen could come in and share here. Another one could come in, let's say, share there. So you can imagine it being kind of like this. So when you're done, what's happened? Well, now hydrogen is happy because hydrogen has its structure we call the duet, right? So it's got 2 electrons by it, right? So it's just like helium. See that? And oxygen has its 8. So it's just like neon. So in the end, they're all happy. They each have as many electrons by them as the nearest noble gas. But they did it though via sharing electrons instead of transferring. You see that? Okay, so yeah, so each hydrogen has a duet, which is, like I said, is the same as helium. The oxygen has an octet, just like neon in this case. Okay, so they did that with sharing. So that's the difference, right? Not transferring, we're sharing. Okay, awesome, I just showed you that. So now the electrons that are here in the middle, in between the two atoms, these in here and these in here, between them, we call those bonding pairs. So that's what makes that covalent bond I was talking about. So you will oftentimes replace that little pair of electrons with a line, and you would write the formula like this. And you keep the little dots here for these. So whenever you see that little line, that's the bond, and that means two electrons being shared in the bonding pair. Now the pairs out here that are not being shared, well, those you can see are called lone pairs. They're also sometimes called non-bonding pairs. Let me try that again. It's not going to fit. Non-bonding pairs. Because we have bonding pairs and we have non-bonding pairs. So the ones in between the atoms that are actually linking them, where they're actually sharing electrons, so sharing electrons, because they are each reaching out, like I said, in a sense then, and holding hands, that's the bond. That's the bonding pair. The ones that are just out here by themselves, not in between atoms, those are the non-bonding pairs or the lone pairs. All of these are important. So you got that written down? Okay. So I'm just going to skip this. Let's just look here. Okay, so if you only share one pair of electrons between them, like let's say hydrogen bond hydrogen, well, that's called a single bond. So that means, okay, I've shared two electrons. Two valence electrons have been shared. But sometimes though, you can also share more than one pair. Maybe you share two pairs of electrons. Like, for example, oxygen does this. So oxygen likes to share two pairs of electrons with another oxygen. So remember I told you, I don't know, like last week or two, there are 7 elements that are called the diatomics. And those elements in nature, they always appear with a buddy, right? So remember, so I said, so H is never just H, it's H2. O is never just O, it's O2. Well, now we see why it's O2. Because if it was just O by itself, well then O by itself is going to be short 2 electrons, so it's not going to be happy. So one O that's short 2 holds out 2 hands. Another O that's short 2 comes over, holds out 2 hands, and they grab hands and make 2 bonds between them. So now they're happy. So that's called a double bond. So 2 bonds means we're sharing 2 pairs or 4 total electrons. And you can also do it 3 times. You can make a triple bond. So remember we said, for example, nitrogen is another one of those diatomics. So if you find nitrogen then on your table, it's in group 5. So it's 3 electrons short. So it would love to make 3 bonds. So what it does is it offers out, again, 3 electrons to a buddy. Another one offers 3. They come together, and they share 3 pairs, which is also written as 3 bonds, a triple bond. So that's 6 electrons being shared. Okay, so these are all sharing electrons. So I want to go through a little system here showing you how to figure out these structures. Seems to be still writing, so I'm going to pause a second. Okay. Okay, so I want you to write down these 5 steps because we're going to use them in lecture, we're going to use them in lab. So just write down the 5 steps to drawing the structure. So these are called Lewis structures. So same as before, we had the Lewis dot structure just for the individual atoms. Now we're going to actually make whole molecules with 2, 3, 4, 5 atoms in them. And using Lewis structures, we can figure out then what's the actual connection between the molecules. Not just CO3, but how is the carbon actually bonded to the oxygens? Is it a straight line? Is it a square? Is it a triangle? What's it look like? So we're going to figure that up now. using these. So step 1 says, determine the total number of the valence electrons. Again, not the total electrons, the valence ones, the ones in the outer shell, the ones that are being used in the bonding. So let's just do this. So we're going to use NF3 as our example. So how many valence electrons does nitrogen have? Not total, valence. It's in group 5, so it's got 5, right? How many valence electrons does each fluorine give? It's in 7, so it gives 7. So 3 times 7. So how many total do I have? Yeah, 5 plus 21. Yeah. So that means I have 26 valence electrons that I have to account for in this structure. So at the very end, when I'm all done, there better be 26 electrons in that structure. Some will be bonding, some will be non-bonding or lone pairs. That's step 1. You got that written down? Okay. So next question is, well, how do I know where to even start for the connections? I mean, so I have 4 atoms, so where do I even start to connect them? Well, the first little sub-rule is, normally, whatever element in the formula only appears one time, that's normally the element that goes in the middle, in the center of the molecule. So rule 2 says, okay, so just lay out the elements in a little arrangement. Well, how do I know how to arrange it? Well, put the one by itself in the center, and then everything else around it. So that's rule 2A, because there's a few little other possibilities. So the element that only appears once is normally the central atom. Okay, rule 2B says, if you have a compound with hydrogen, oxygen, and some other element, then that some other element is the center atom. So let's say it was HNO3. Oh, that's got hydrogen, oxygen, and nitrogen. So the nitrogen's the center. H2SO4. Oh, hydrogen, oxygen, and sulfur. Oh, the sulfur's in the center. So you have a compound that's hydrogen, oxygen, and X. X is the center. So that's the 2B subrule. Okay, 2C. If you have a carbon-containing compound, if there's carbon anywhere in the molecule, carbon's almost always in the center. Regardless of anything else, if it's got carbon, carbon goes in the center. And the last little rule says hydrogen and fluorine will never be in the center, because hydrogen only needs one more electron, so it can only make one bond. So you never find hydrogen in the center trying to make 2 or 3 bonds. Same thing with fluorine. Fluorine only needs 1 electron. It only makes 1 bond. You never have fluorine making 2 or 3 bonds with other atoms. So hydrogen and fluorine will never be in the center. Okay, so you have the 4 little sub-rules. So out of NF3, which element would be in the center then? Again, the one that appears only one time in the formula. So there's only 1 nitrogen. So I would put nitrogen in the center and just put 3 fluorines around it, kind of like this. Just place them around. So draw something like that. Nitrogen, with 3 fluorines kind of evenly spread around it. Just kind of spread them out. Or you could, like a little Y or a triangle kind of. Okay, rule 3. Now we're going to go through and we're going to actually connect all of the atoms with bonds. So we're going to draw a bond between every nitrogen and fluorine. And every bond has how many electrons in it? 2. So for every bond you draw, you're going to subtract 2 electrons out of your total. So in this case, I'm going to draw 1, 2, 3 bonds. See that? So if I draw 3 bonds, how many of my 26 electrons did I just use? I just used 6, right? So I'm going to subtract 6 from my total. That leaves me with 20. So you're going to keep a nice running total here going. So I had 26, now I've used 6, so I still have 20 left to account for. It's going to keep going through until we hit 0. Okay, so we just drew 3 bonds, so that's 6 electrons. Well, I still got 20 electrons left, so what's the next step say? The next step says start to distribute those electrons as lone pairs on all of the atoms on the atoms. Because we know they all want to get up to 8, octet, except for hydrogen, of course. But it does say, a little sub-rule, do it on the peripheral ones first. So don't do this one first, do these first. And save the center one for last. So do the peripheral atoms first. Just start putting on the remaining electrons as lone pairs and try to give them however many they need. Now it says start with the most electronegative element first. You don't really know yet what that is, but you will here in a little bit, so we'll just write that down for now. But basically, start with the peripheral first, do the outside ones first, and then the inside one last if you have any electrons left. So, right now, if you're looking at it, let's just ignore everything else. This fluorine has how many electrons?
It should have 6.
Yeah, well, yeah. Right now, it only has 2, so yes, it needs 6 more, right? So I would give it how many pairs?
3.
I'm going to put 3 pairs on that one, all right? Boom, boom, boom. And the other one needs 6. And the other one needs 6, right? So we're going to give them as many lone pairs as we have to until we get up to their noble gas configuration. How many electrons did that use?
24.
No, well, I mean there and that's 6 and 6 and 6. How many did I just?
18.
Okay, so I just used up 18 more out of my 20, right? So I'm going to subtract 18 from my total. So I had 9 pairs. So I still got 2 left that I have to account for. Well, the next 2b says, don't forget hydrogen can only have 2, right? So don't give it any more than 2. It says if you still have any left, and we do, we still have 2 left, we're going to give them to the center atom. So how many right now does the nitrogen have next to it? How many right now does it have next to it? It's got 6 right now, right? You see that? It's got 2, 4, 6. So it would love to have 2 more. Perfect. So we just give it 2 more. So we use our last 2 and put them on as a lone pair on the center atom. See that? Just put it right there in the center atom. Boom. And then I subtract those 2 off the total. There we go. We've used them all up. And every atom has an octet, has a noble gas configuration. They're all happy. We used all 26, no more, no less. Works out perfect. Isn't it a beautiful thing? I know. Brings a little tear to my eye. It's so pretty. It's the great order of the universe. It all works together. Okay, but I told you there was a 5th step. Right? There was actually 5 steps. So one more step. But I'll let you finish writing that one down. And then we're going to run through these 5 steps a bunch, and lab a bunch too. So, okay, the 5th step. Are you still writing? Okay. So the 5th step says, once you're out of electrons, waiting for Jamila. She's still good. Okay, good. Okay. Make sure the center atom has an octet. If the center atom does not have an octet, that's when we're going to start making double bonds and triple bonds. So if you don't have an octet in the center atom, now we're going to begin to take non-bonding pairs and shuffling them over into bonding pairs and make 2 bonds or 3 bonds, whatever we have to do until every atom has that octet, except, of course, for hydrogen. It only wants 2. So if the atom doesn't have an octet, start making multiple bonds by converting non-bonding pairs, lone pairs, into bonding pairs. Okay, so let me show you a couple examples of these. Once you get it written down there. Okay, let's try an example. Okay, let's try SO2. Let's try SO2 on here. So sulfur dioxide, SO2. So let's just go through our 5 steps. Step 1 says, add up the total number of valence electrons. So how many valence electrons does the one sulfur give me? It gives me 6, right? It's in group 6. Then I have 2 oxygens. How many does each oxygen give me? How many? Oxygen's also in group 6, so yeah, that's 12. So I have a total of how many electrons to account for?
18.
Okay, so I got to account for 18 electrons in my structure, right? Okay, which element will go in the center, sulfur or oxygen? Why sulfur? Convince me. Yeah, the one that only appears one time, that's by itself. So I'm going to put sulfur in the center, and then I'll just put oxygens around it. Just, again, just kind of spread them around evenly, opposite sides, left, right, top, bottom, something like that. Okay, that's step 2. Step 3 said, connect the atoms with a single bond. So I'm going to draw a bond here. I'm going to draw a bond here. How many electrons did making 2 bonds just use up? I just used 4, right? So I'm going to subtract 4 from my total. I still have 14 left. So, yeah, so keep a little running total like this going, I'm telling you. That's the way to do it. Just subtract 12, or add 12, or subtract 4, whatever. Just keep a little total going. Okay. Now, step 4 said, take the extra ones you got left and start giving them out as lone pairs on the outside atoms first until you get an octet. So, how many more electrons does each oxygen on the outside need? Okay, right now they each have 2, so they each need 6 more. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So how many of my 14 did I just use? 12. I still have 2 left, so we're not done until they're all gone. So then it says, if you still have some left, put them on the center atom. So how many do I put in the center atom? 2. Now sometimes students say, oh, well, it needs 4, and they'll put 4 on there, but I can't. There's only 2 left, right? So you can't put more than you have. So I'm just going to put the 2 I have left on there. And now I've used my last 2. I'm out of space here, but there, we're done. We've got 0 left, right? Okay, so here's where step 5 comes in. Step 5 says, make sure your center atom has an octet. Does it have an octet? It doesn't. Sulfur only has how many right now? 6. So it's not happy. So we have to make it happy. So we are going to take one of the non-bonding pairs on the oxygens, migrate it over, and make it into a bonding pair. So I have 6 options, right? I could do any of these. It does not matter. They're all the same. I can do any of these I want. I'll just pick this one. I'm going to move it over here and make that into another bond. And then this goes away. So I moved the non-bonding pair and made it into a bonding pair. See how I did that? Maybe. So now, how many electrons are around that left oxygen? Right here. How many are there? 8. It's happy. How many are there around the sulfur now? 8. All right. 2. Single bond has 2. Lone pair is 2. Double bond's 4. It has 8. How many are there around this sulfur? There's oxygen now. 8. Right? So they're all happy. So see how that worked out? So everybody got an octet in the end. They were all happy. Okay. Now, however, though, you might have noticed, let me do a little erasing real quick here. We had two options, though, on that. Once I had the sulfur here, draw this real quick again. I could have taken a lone pair off the right oxygen or off the left oxygen. I could have done it off either oxygen. There was two options. So I could have done it off of here and made a double bond here. Or I could have done it like we did off of the right one. Made a double bond on that one. See that? So that's what I'm referring to above that, which is called a resonance structure. So you have basically the same arrangement of atoms, but different arrangement of electrons. So I could have done it either the left way or the right way. So both of these are what is actually occurring, because nature is not picking between the two. Both of these are occurring. So these are both possible structures. These are called resonance structures. We had more than one option, so I have more than one correct structure. So you would actually write both structures. And the way you show their resonance is you put that little arrow between, in between them, on this little arrow here with two heads on it. That's called a resonance arrow, a little double-headed arrow like that.
So if we were doing our homework and you said to draw a resonance structure, we would draw it just like that. We would put the...
Yeah, so you just
Okay.
draw like that with a little double-headed arrow like that between it. And that means, aha! It's actually both of these are occurring in nature. So actually what's happening in nature is it's actually kind of going back and forth. It's a hybrid, actually. It's not really this or this. It's kind of a hybrid where it's not 1 or 2 or 2 or 1. It's really more like 1.5, 1.5. It's kind of like like spread out as a hybrid. And come back in 110 if you want. We'll discuss that in greater depth. Okay, well, let's try a couple of these. Let's go through our 5 steps. Go through those steps with me. Let's do H2S together. So I'm going to work through all the steps, nice and slow. So step 1 says, add up the valence electrons. So how many valence electrons do I get from each hydrogen? So I have 2 hydrogens. Each of those gives me 1. That's a total of 2 electrons, right? I have 1 sulfur. How many does that 1 sulfur give me? 6. It's in group 6. I have a total of 8 electrons to account for, right? Okay, thank you. Thank you, Austin, for nodding. Okay, so which element goes in the center, hydrogen or sulfur? Okay, sulfur goes in the center for 2 reasons. One is sulfur only appears 1 time in these. Plus, we know hydrogen can never be in the center. Ever, ever, ever be in the center. So I'm just going to put sulfur in the center. And then the hydrogens, I'll just kind of spread them out. There's no real right or wrong way. Just kind of spread them out like this, you know, one on each side. Okay. Step 3 says connect the atoms now with a bond. So I'm going to draw 1 bond, 1 bond. How many electrons did I just use by making 2 bonds? 4. So how many do I have left? 4. Now I'm going to give you a warning, which you will see again in lab. Go through the 5 steps. Students always just want to try to jump ahead and do shortcuts and say, oh, okay, well, lone pair, lone pair, lone pair. They just give everything lone pairs, and then they miss out then on the multiple bonds and things like that. So I'm just telling you, just go through the steps. It's not really that long a process. Go through the steps. It'll save you much headache. Step 4 says, now take the remaining ones and give them out as lone pairs. First to the peripheral atoms, then if you have any left, to the center atoms. How many more electrons do the hydrogens want?
None.
They don't want any more, right? They already got their 2. They're happy. So don't give hydrogens a bunch of electrons trying to give them octets. Yes, hydrogens only want 2 to be like helium. So I still have 4 left. Well, I'm going to put them on the center atom. How many more does sulfur want?
4.
Oh, it wants 4, right? It's got 4, it wants 4. So I'm going to put 1, 2, 3, 4. Subtract the last 4, and I have 0. And the last step says, make sure the center atom has an octet. Does the center atom have 8? Yes. We're happy. It's done. The universe keeps on spinning. Okay. Let's try the next one. I'll do SiF4 with you. So SiF4, so let's add up all the valence electrons. So 1 silicon, how many electrons does 1 silicon give me? 4. And then 4 fluorine. How many does 4 fluorines give me?
28.
Yeah, 7 each, so 28. So how many total valence electrons? 32 to account for. Okay, great. Awesome. So which element goes in the center? Silicon, right? Because it's the one that appears one time in the formula. So we'll just spread the 4 fluorines around, right? Left, right, top, bottom, or 4 corners of a square, whatever you want to do. Just spread them around somehow. Again, there's really not a right or wrong way yet on this. Okay? What's the next step?
Distribute the remaining electrons.
Oh, not yet. One more thing.
Subtract 8.
Why?
Because you make 4 bonds.
Make 4 bonds first, right? Connect them with bonds. Make 4 bonds. Every bond uses 2, so then I subtract. Subtract 8. So I have how many left?
6.
24. One of those math things. Okay, so I've got 24 left. Okay, so now I'm going to distribute those remaining 24 as lone pairs, starting with the peripheral atoms first and then the center atom last. So how many more electrons does each fluorine need? Each fluorine only has 2 right now from the bond, so they need 6 more, yes. So I'm going to do a whole bunch of dot drawing here. Stupid iPad. Okay, how many electrons did I just use in lone pairs?
24.
6, 6, 6, and 6. Yes, I used 24. So I'm all out. So I have none left for the center atom. So it says, just check and make sure the center atom has an octet. Does the silicon have an 8? It does. So again, we're done. I'm telling you, it's really not that bad. You just got to work through the steps. Just got to go through it step by step. Okay, your turn. Try PCl3 with your neighbor. Talk it over with your neighbor. Add up the valence electrons. See what you think. Figure out which one goes in the center. Start making your bonds first, then your lone pairs, then any multiple bonds if you need to. You get something that looks like this. Each chlorine has 3 lone pairs. Mine are really ugly, but... And then 2 left, so I put them on the phosphorus. Is that what you got? Something like that? Yes? Okay. Now CS2, again, you got to follow those steps. Don't just start giving everything octets because you're going to run out of electrons before you get them all applied. So let's just run through CS2 together. So, how many total valence electrons do you have for CS2? Right, so the carbon gives 4, so that's the 2 sulfurs each give 6, that's 12, so yes, 16 valence electrons. Which one goes in the center? Yeah, rule 2C, anytime you have carbon, carbon goes in the center, regardless of if it's by itself or not. If you got carbon, it goes in the center. Put the 2 sulfurs around. Make 2 bonds, that used 4. I got 12 left. Put them on as lone pairs. 2, 4, 6, 8, 10, 12. I'm out of electrons. However, my carbon still doesn't have an octet. So I got to start doing some shuffling and take non-bonding pairs and turn them into bonding pairs. The question is, do I take one from each sulfur or two from one and none from the other? Well, normally the way it works is it's always best to try and make things as symmetrical as possible. And there is a whole actual way, let's actually calculate that, called formal charges, but I won't show you that. Come back at 110, I'll show you that. But for now, just kind of keep in mind, symmetry is key. So rather than do a single and a triple, normally better to do two doubles. So I'm going to take this lone pair right here and move it over here. Shoop. So I moved one over here. And take this lone pair here, let's just say, and move it and make another bond. Okay? There you go. Now everything has 8 when I'm done, right? So sulfur has 8, carbon has 8, sulfur has 8. Everybody's happy. Okay. Last one, I'm going to do real quick. Notice it has a negative charge. If an element or an ion has a negative charge, what's that mean happen? It means it gained an electron, right? It's negative. So you're going to add up nitrogens and 3 oxygens, then you're going to put one more because it gained a negative charge. If it was 2 negative, you'd add 2 more onto your total, or 3 negative, you'd add 3 more onto your total. If it was positive, just the opposite, right? So positive means it lost an electron, so you would subtract 1 for your total. So add 1 valence electron for every negative charge. Subtract 1 for every positive charge. So in this case, I've got a nitrogen, and that gives me 5. I've got 3 oxygens. That gives me how many? 18. And then I have a 1 negative charge, which gives me 1 more. So I have 24. So a very common mistake is students think, oh, it's 1 negative, so I must, subtract 1 because it's negative. No. 1 negative means you actually gained an electron, so add 1 onto the total. Okay, so then you start drawing your structure, and you get something like this. And then you're short, so you have to make a double bond. The question is, do you use the top left, the top right, or the bottom one? Doesn't matter. You're going to do all 3. So you're going to draw 3 resonance structures. So I'm going to erase all of this mess here and make a bigger eraser. This will be here all day. So it could have been this one, yes. Or it could have been the other one. Or it could have been the other one, which I don't have room to write on here, because I'll put it down here. Sorry, that's really messy, and I should have a little double-headed arrow between here too. The only other thing you have to do with ions is I gotta show the charge on that. So the way you show the charge is you're going to put big square brackets around the formula and put the charge up here in the corner. So it's 1, why is my 1 negative not showing up? Oh, there it is. If it was 2 plus, I'd put a little 2 plus up there. So you just put square brackets around it and put the charge, and that shows you the charge. Yes?
So if it was like a 1 plus from the beginning, would you have to
subtract 1 from the total? Yes, you add 1 for every negative charge, subtract 1 for every positive charge. So if it was something 3 plus, I subtract 3 off the total. If it was 3 negative, I'd add 3 onto the total. Yeah.
And so you said carbon's always going in the middle, even if not by itself? So
Yep.
So what's something, how many draws does 2 carbons?
Well, I mean, it depends on the rest of the structure, what it's with. But yeah. It'll be 1 carbon, and then it'll probably be like carbon, but anyway. But you'll see that maybe later on here. Okay, so this lab today is basically doing lots of this. We're going to draw a bunch of these, and we're also going to discuss stuff called polarity and shape, which we haven't gotten to, so we're going to lecture first thing in lab. So go ahead and just keep your notebooks handy, and we'll lecture. So we'll be over there. We're getting out a little late, so let's say, roughly 3:30, maybe 3:35. If you want to have a little quick break. We'll be there about 13 minutes then. We'll finish up the lecture.
So does that mean we put
Yeah, I was
this
football
next?